In some of the situations, you're gonna have different emotions, and those emotions could be represented by the facial expressions. We all know that we want to be faster children, and we want to find if there exists some technology which could generate multiple emotions just from one single picture taken by us. Today we will discuss more on anatomically aware facial animation from a single image. For example, when you are about to attend the high-table dinner, you might feel happy, fresh, and even kind of excited. And this time, our program could generate a smirk for the image, which makes the emotion more smirky and hot. Then, when you go to the Disneyland, you hold Winnie the Pooh and take a picture with a smile. What about adding wink to it? We can add this wink using our program. Also, when you go to the harbor city, you take a rest and release. For this program, it represents a differentiable render capable of changing the expression of a person, not from training and just from a single image. To do this, the program has two main components. The first one is a self-learned face attention, which is capable of focusing into specific parts of the face. And the second part is the anatomically aware expression representation, which does not require a 3D face model nor an initialization method. Finally, the entire method is trained in an unsupervised manner.
In order to achieve anatomically aware facial animation, there are two key components we have to discuss first. The first one is the expression representation, also called continuous anatomically aware representation. The second one is the generation mechanism, also called self-learned face attention. For the first key component, our goal is to find a way to represent different expressions. We do not use discrete emotion categories like previous works, but instead, we use action units defined by the fact system. Every action unit is directly related to some facial muscles. We encode our expression as a vector. Every element in the vector represents a level of contraction of a muscle on the face. For example, to contract a happy expression, we have to control muscles related to action unit 6, 12, and 25. And we can control the level of happiness by changing the level of contraction of these muscles. Here are the results when changing one action unit at a time with different levels of intensity. To generate more complex expressions, we need a combination of different action units. The second key component is image generator. Normal generators would regress all the pixel values from the output image, but we only want the pixels that are directly related to the expression be changed. For example, if we want the eyes to be closed, we just want to change the pixels around the eyes. And we simply copy other pixels from the original image. We embedded a self-learning attention mechanism, which is training in a completely unsupervised manner. For example, here we want to generate a smile expression. The attention mechanism is forcing the generator to only change those pixels with darker activation values in the attention mask. And the blacker the pixel is, the more important it is to generate the desired facial expression. The rest of the pixels will be directly copied from the original.
Okay, when it comes to training, it's getting more complicated. There are additional losses need to be considered in training. There are 4 losses presented in the paper: image adversary loss, attention loss, conditioning expression loss, and identity loss. I'm going to explain those losses in a more graphical way so that we can have better understanding in them. Image adversary loss. The paper applied a modification of the standard GAN algorithm. Same as all GAN algorithms, a generator and discriminator are needed. The generator G can generate the realistic images we want, and the discriminator D tries to tell the fake one apart. In this well-developed data model, image adversary loss is introduced to learn the generator's parameters. Attention loss. When generating images, we should make generator only focus on those regions that are responsible for synthesizing the novel expression. How can we achieve this? This paper introduced attention mechanism. Concretely, the generator output two masks, a color mask and an attention mask. We get final image by proportionally combine color mask and original image, according to the grayscale of the attention mask. In order to prevent the attention mechanism from saturating, a penalty of attention mechanism is needed. Conditioning expression loss. The paper also included an expression regressor to penalize the differences between the desired expression and the generated one. This gives guarantee on the correctness of the generated expression. Identity loss. Obviously, we don't want a correct expression but with wrong face, so they also further added a cycle consistency loss. This will help the generator to maintain the identity of the imposed image.
To conclude, we have presented here a differentiable render capable of changing the expression of a person, not producing unchaining and only from a single image. To do this, we have two key components. The first one is a self-learning attention mechanism that helps us transition between real and fake patches of the image and an anatomically aware expression representation, which does not require to feed any 3D face model, nor initialize our method, and the entire method was trained in an unsupervised way. Also, we have shown that our model is robust to images in the wild. Next, let me show you some examples on how we train the model and how does it really works.
We visualize our training progress, and after 36 hours training, this is our testing result.